Okay, let's go now. Let's continue our discussion on fuzzy logic control and applications, which hopefully will be very helpful to you for both your experiment number 3 as well as possibly some project. So another thing that you can do is to actually have your robot here. You may have it planned to go through, navigate through some path. You have a desired path. You have the current path, and then the error will be acted upon by actuators to actually run the robot. This could be actually this controller box here could be coming with a manufactured robot already. So this could be a PD controller on the robot, like the Pioneer robot or Turtle robot in the lab. And instantly you get a chance to work on either one of those 2 robots in the lab. And then you can also use this tracking error to excite some adaptation algorithm to control this controller, so to speak, to adapt this controller to the changes on the path in the middle of the navigation. As we said briefly in chapter 5 last hour, when the robot moves from A to B, sometimes it's possible to run into some unforeseen situation. Maybe something came in the path of the robot. The robot has to be able to adjust itself. Okay, and it's also possible that the robot may have a change in its dynamics. For example, if a robot has a big load on it, mobile robot, and it clears part of it and moves on, that robot has changed its mass, the central gravity has changed, the mathematical model has changed. Therefore, the original controller may not be good enough. So you can do this supervisory loop, which is right here. This is the supervisory loop. You can do to adjust the parameters of the controller H of t. So now let me move to another chapter. Also, you need to perhaps take a look at the fact that in this diagram, you see what we call 2 control surfaces. This control surface is done by classical logic rules, if-then rule, which are crisp. This is done by fuzzy logic. Same control problem, but it's done by fuzzy logic rules. As you can see, the transition between one level of logic to another is quite sharp. Long distances and vertically distant. Here, you have it in a gradual transition from one level to another level. Okay? And in order, the cost of this one, if you put some price and cost on every movement of on this control surface, here is more expensive than this one. For the same reason, the robot going from point A to B, you go to horizontal, vertical, or instead of go straight. Same thing. Okay. All right. So let me now go to another chapter, which is the real-time fuzzy logic controller. This has to do with fuzzy logic control of a laser beam, which one of our students in the class was in my previous class and tried to run it with fuzzy logic controller. I think he managed not to do it. I managed not to do it for some reason. I think he ran out of time and possibly needed more help. But anyhow, this is a couple of my students. Actually, one of my students, Richard Marchbanks from Los Alamos National Lab in New Mexico. He has the following system. He has the following system. You have a laser. The laser is shining on a mirror. The mirror gets bounced and goes to a detector and then creates a difference between where the laser has to point in that detection process compared to where it is right now, gives you some kind of detection error. And that goes through analog digital converter, goes to the controllers. And that controller, fuzzy logic controller, you saw that in a bunch of inference engine rules, if-then rules. It goes to digital to analog, and then goes to a motor which moves the mirror in such a direction that the laser points exactly on the target. So this is a laser pointing control system. Okay? And actually he ran it he put the whole thing in real-time hardware. And I even have videos of this experiment. I have to convert it from old VCR into DVD now, and I'll try to show it to you later. So he talks about the hardware, and here you can. This is the characteristic of the motor, which has a dead band. It's a nonlinear characteristic, and this is a armature voltage, which also has a dead band here. So the motor is actually going to be a nonlinear device. It's not as simple as a DC motor. The software is an old software, of course, from the old times, and what you can see here is that the error, these are the membership functions of input error, input change in error, and output armature voltage. As you can see, you feed back the error and you compute the derivative of the error. Those are your two sensory information. Each of them have at least 3 membership functions. So here you have a trapezoid membership function, a triangular here, another triangle here, and another trapezoid. So you have 5 different membership functions. It's always a good practice to choose odd number of membership functions. You choose one to be right at the 0, as you can see. You have 1 here at 0, then 1 here, 1 there. You have 1, 0, which is here, 2 this side, 2 that side. This is 5, this is 3, this is also 5. So the first thing you want to do is to put fuzzy membership function for the input to the controller and the output of the controller. Of course, the input of the controller or the output of the system, okay? Which in this case is the error in the location of the laser on the target. And then, for example, you have NM for negative medium, NS negative small, 0, positive small, positive medium. You use your own linguistic terms. And then you have here 2 what we call fuzzy associated memories, FAM, F-A-M. You have 3 you have 3 membership functions for the output and 5 membership functions for the error. I'm sorry, 3 for the change of error and 5 for this. So combining error, if error is something and the change of error is something else, then the output is something. They're all linguistic. You can see that when you have 5 membership functions and 3 combining into the controller, your maximum number of rules is 5 times 3, 15 rules. So here's a full set of rules. So Richard had to compose 12 rules for this initial control system. However, many times you are confronted with what we call curse of dimensionality. If you have a lot of variables, then if you multiply them together, it becomes huge. Okay? You could have thousands of rules, which makes no sense. But in this case, it's only 15. But even that, you have reduced it to 7 rules. Purundi. The most important part of the rules are the ones which are in the diagonal element, or upper, these ones. So he basically is like this. If the laser spot is on the left side and moving to the right, leave it alone. Put 0 control on, because it's coming back to where you want it to be. If the error is negative and the change of error is also negative, you give a big positive control, bring it back. So a lot of these rules are common sense, are intuitive as you learn about that system. That's why I want you to do simulation before you go to the lab, so you get practice in composing the rules. Okay? So anyhow, Richard did 2 sets of rules, in other words, 2 fuzzy logic controllers. So here is, for example, is where you want to be right in the middle of the target. And here you have an error which is positive, you want to move it to the left. So this is called center finding, and B is tracking. So look at this response. This is an actual experimental response. It's not simulation. You see a curve here is a pruned error due to the pruned set of rules. This X is for X location of the laser pointer on the detector, and this is the Y position. Okay. So center finding with non-fuzzy, sorry about that. This is non-fuzzy proportional feedback. Okay. I think that F is wrong. PF shouldn't be there. Designation is wrong. So this is actually crisp control. Okay, it's like a PD control. When you feed back the error, the change of error is the same as PD control. Now look at this. Here you have the solid line is regular non-fuzzy control, proportional feedback, and the dotted line is fuzzy. You can see the difference? It's much better controller, much less undershoot here, much less undershoot. And here you have 3 values. You have error in the X direction. You have the regular one, the pruned one, and the full set rule. As you can expect, when you have the full set of rules, you have a better control performance because you're paying the price for it. More computation. So center finding with proportional feedback, fuzzy feedback, and prune fuzzy feedback. Okay. Now let me go to another. By the way, the appendix in that chapter shows all the membership functions and all the rules. If error is positive medium, and the change error is 0, then the speed is negative medium, and so forth and so on. Now let's look at another chapter. This chapter, chapter 13, is also a couple of students from Los Alamos. These students actually were professionals. They had full-time jobs there. And they were able to use their knowledge of this course to do something in the lab in Los Alamos, New Mexico. Simulation of traffic flow and control using fuzzy and conventional method. This is application of fuzzy logic to do switching light, yellow, red, and green on the traffic signal. So they had to model the dynamic model of the vehicle, which is on these equations. And they, of course, started simple. They look at one intersection, like this. Okay. And as you can see, there are 2 lanes in each direction. There are several ways each vehicle can go to the right, can go to the left, can go straight. Okay, so there are several options you have. So they gave a cost function with the wait time behind the red light, and then the number of cars going out and the number of cars coming into the intersection. Okay. So derived mean is the average derived time, wait is the average waiting time, and so forth. So they put some parameters and they put fuzzy values on those values. For example, this is membership function for green lights. It could be 0, it could be low, medium, and high. The amount of time that you designate for the green light. These are membership functions for red light, for time, waiting for the change, and the membership function for the change itself. So you are driving, you get into a red light and you're waiting. So your wait time and the movement of the switching of the red light, the time that is green, the time which is red, is all part of the input into the controller. So then what they did, they actually went to the village of Los Alamos and got traffic data from the city, from the village, and used that information to come with compose rules for it. Okay. And they looked at 625 different combinations of simulations were useful in identifying the strength and weakness of the fuzzy controller. Using this information, we were able to modify aspects of the fuzzy controller and improve its performance. The data in the live simulation and the corresponding results are more interesting because they provide a real world example. Okay, so this diagram shows the number of cars going through a sequence of 24 hours, east, west, and north, south, 2 directions. And this one shows the control performance comparison, fuzzy, proximity, and time. When you sit behind traffic light, normally the traffic control system, as it used to be, now more and more advances are there. The more advanced in sensing, it helps the control. It helps the decision making. You go in front of a red light and there is no car in the other direction, but you still have to wait. Okay? That brings me to a true story. One time I was actually lecturing on fuzzy logic in Saudi Arabia. And I arrived in Riyadh, the capital, about close to midnight. And some graduate students from the university was waiting for me in the airport, and he took me to my hotel. And it was almost 1 o'clock in the morning by the time we cleared the immigration and the customs, etc., etc. And he was going so fast, and he was just going through red light one after another, one after another. And I was saying, oh my God, where's the seatbelt? You know, I'm looking at the seatbelt. And so the problem with that intersection in the city of Riyadh was that they had no fuzzy logic or intelligence in those intersections. Because with this kind of simulation, with fuzzy logic playing a big role in human decision making, when there is no traffic there after the time, it switches automatically.
7 seconds.
Yeah,
7 seconds here. After 7 seconds, they change the lights in here.
Okay, yeah, I was said that here is about 7 seconds that change light. Now, in some of the cities, like I've seen it in Hawaii and some other cities, when your car goes through the intersection and the heavy front of the car comes on a part of the asphalt, which is actually sensor under the asphalt. And that sensing information is very important to alert the traffic controller to switch. There is no need for you to wait anymore. Okay. And then, of course, as you notice attached to the bar which holds the red light for you, there are some sensors which once you come in, the sensor picks you up. Another car comes, it picks you up, and then it accumulates how many you have, then switches you. Okay? And during the time of the day, some switching is much slower, means when you have traffic, heavy time of the day, so-called rush hours, but then late at night becomes much different.
It's also really important for oil consumption.
Of course, it's very important from 2 points of view. If you spend a lot of time behind the red light unnecessarily, you are spending too much gas and you are polluting air at the same time. So you are damaging both your pocket and the air. Okay? So that experiment also is on a video, and I'll try to find it for you. And they actually had simulation of that. This is another chapter done by 2 of my master students. And this is a very interesting problem. These 2 students came to my office one day, Erlander and Kenneth. Dennis. Kenneth was not my student. Dennis and Erlander came to my office. Both of them were 2 of my master students. Dennis was from Yugoslavia, and Erlander was from Iceland. He's my only Icelandic student in 125 student of class. One Icelandic student. Okay. They came to my office and said, we enjoyed this course and we want to do fuzzy logic control, because both of them were inclined toward power systems, electric machines. We want to use fuzzy logic control for electric machines, for generator, power generator. I said, okay, go to the 10th floor, there is a inventory room, a whole bunch of old machines and DC and AC machines, generators are all there. Pick your machine and bring it to the ACE lab. Even then we had the ACE lab. And they found one and it was full of dust, they cleaned it, and then they said, we want to simulate a model for it and then go to the lab and do real-time control, which is a reasonable thing to do, like I'm doing now, having you do a homework on simulation and then go to the lab. They went to the library. There was no internet. There was no Google. There was no Wikipedia. There was nothing there. They had to go to books and journals. And they looked and looked and looked. They found a gigantic nonlinear model, 9th order nonlinear model, which was too complicated for really to work with it. And they said, do you have any other choice? Do you have any other advice for us? I said, okay, how much do you guys already know about these machines? Have you ever had a real experimental course that you work with them in the lab? One of them did, one of them did not. I said, okay, put yourself in the place of an operator for this system. Clean them up, connect them together, run them open loop, put a bunch of input for, let's say, rotational velocity of the motor running it. You had a motor and a generator aligned on the same shaft. Okay, in fact, let me see if I can show you the system. Yeah, see, they have a DC motor. They had a DC motor and an AC generator. The DC motor is like the turbine. It acts like moving the shaft of a generator inside a magnetic field to generate electricity. Okay. It's essentially laboratory style of produce electricity in the lab. Okay. So they connect them together and they run over this part of it first. And they play with regular controller or different voltages and different feedback values. They played with this machine enough time, after a couple of weeks, they became quote-unquote expert for that machine, whose model was so complicated they gave up on it. So based on their own experience with this machine, they were able to compose the rules. Okay? They made a lot of notes and they made a lot of observation, they came up with the rules. So you have many, many alternatives to come with your rules. In one of my books, not this one, another book, I have 5 different ways you can come up with a rule. One is to simulate it if you have the model. Don't throw away the model if you have a good, accurate model. Simulate the heck out of the system. Through the simulation, you gain knowledge. Or you go and ask someone who knows that system and interview that expert and come up with a bunch of rules. Learn from the expert. If in the absence of an expert or an operator, you do it yourself. Okay? And if you don't have any of that, a fourth option is to come up with the input and output data of your system in an open loop and put it on neural network or fuzzy logic to come up with a nonlinear mapping or model for it. Then you can design a control around it. Okay? So, and of course, nowadays, the machine learning is a very popular area, and you just give me the data, I'll give you the model. Okay? So this is the actual hardware experiment in the lab, the setup. You have a fuzzy logic controller. It's all on a computer in the dash line. You have two digital to analog converter, two analog digital converter. You have frequency measurement, voltage measurement. You have a transformer here, and you have a control circuit here and a control circuit here. So they close the loop and they actually run the experiment. And this is the DC motor with compound winding. That's the synchronous generator. And this is the control. Actually, they had initially they have the control circuitry here. They did the measurements, and then they went to a bunch of rules that they did themselves. These rules are the rules that they ran through it. About 9 of the 9 rules, this is the result of 2 weeks of working with the machine. Okay. And needless to say, this chapter made it into the thesis of both of them on 2 different aspects of this project. Okay. That's why I've been guiding all my ACE students who are in this course and my other course. The projects they do in the lab, in the course, can actually, if it's good enough, it finds its way to the thesis later on. Okay? So, if that's not incentive, what is it? Okay. So, again, these are the membership functions for input values of controller, frequency counts, voltage counts, and membership functions for controller using 8-bit digital to analog converter and shunt current and so forth. And then they did the experiment. And these are the actual experimental results. This is the actual experimental result of the response, frequency response for 8 and 12-bit, 2 different kind of converters. Okay. More of that voltage plots and control signal plots. Okay. So these 3 chapters I showed you are only 3 possible examples that you can do in this particular course, and I will provide you with a problem. Maybe we'll do a mobile robot that you are now running them in the homework number 3 using those toolboxes of the author. But we want to simulate fuzzy logic controller on those. And we will give you additional material based on what Dr. Benavides and Mr. Errol will provide us. And then we will have you use those new software. The one which is, I think it's called Fuzzy Light or Light Fuzzy or something like that. It's similar to Fuzzy Logic MATLAB toolbox, but it's more amenable to real-time control. So you might as well get used to that. You can use it later on. So let me see if there's anything else I need to bring to your attention before I sign off. I think that is it. So this particular book that you see here, it actually has more chapters. It has a raisin control in manufacturing plant. It has pattern recognition chapter using fuzzy logic. Okay. So there are many other possibilities there. I believe that book also was translated into at least one other language, maybe Mandarin, I'm not sure. But nevertheless, help yourself if you don't have it. What I showed you was only 15 chapters. There are more chapters in this download. So I want to again summarize what we said today in the 3 sessions. We are in chapter 5 of the book, using non-path planning and path plan navigation. I owe you one more navigation using cell technology and the Voronezh vehicles. And then we talked about fuzzy logic control system, how to set up membership functions, look at the input and output of your controller, put them into a universe of discourse from a minimum to a maximum value, put an odd number of membership functions between the 2 ranges, and then create knowledge. One way or the other, come up knowledge. Either you have it or you may have to secure it or seek it and find it. Okay? And you may even be able to find rules on the internet. Okay? But if you do, give proper reference to where you found it. Okay? Okay, in that case, we will see you next week, and thank you very much.